So we were discussing in the first part regarding the various expressions for the strain energy associated with different kinds of loading like axial loading, bending moment, transverse shear, torsion, and these are the kind of things which we'll have to pick up while solving problems. But the question is that while solving problems, what is the nature of the problems we are going to try to solve? Our primary goal uh, or one of our primary goals will be to determine the deflections associated with a given set of loadings on a beam, on a shaft, these kinds of things. Okay, so to boil down to its essence, uh, we are interested in determining the deflections. Please note that earlier we have already done an entire chapter on deflection of beams. Okay, that was using differential equations as our method to in that chapter we use the differential equations as a method for obtaining the deflections, but you will see here that we can bypass uh, the the use of differential equations. Okay, so now uh, in the very beginning of Monday's lecture, I had stated and I had discussed with you that when we say energy methods, uh, we are kind of familiar with energy methods from our discussions of conservation of energy, which we studied in our +2 mechanics as part of physics. Now, we wish to go beyond that, which means that there must be something missing from the conservation of energy principle which we want to address, which is why we want to go for more advanced things here. So the name of the topic for our next discussion will be this. Okay, the name of our next topic is limitations of conservation of energy principle. Now, I can go into a general description of the theory and whatnot, but I think it is more useful to the students if I directly demonstrate what is the utility of the conservation of energy principle in terms of the kinds of problems that we are doing, and then to illustrate to you where is the difficulty using this conservation of energy principle. So instead of talking about general theory, let me just illustrate to you. Okay, so our favorite example is the cantilever beam. So we'll take that once more. And we apply a point loading at its tip. And the question which we ask ourselves is the same question which we had asked earlier in the context of studying the previous chapter on the earlier chapter on deflection of beams, is that what is the deflection at this end? And let us see, using this conservation of energy principle, um, basically the balance of work and energy, if it is possible to determine the deflection here. Okay, so what we'll say is that, okay, so if this force is P, then we have already seen that the work done due to this force will be half of the value of this force times the deflection which will be undergone by the point of application of this force. So this is the work done, which we keep on our left hand side of the equation. On the right hand side, we should be writing the strain energy because remember that we are actually trying to use the W is equal to delta U, that equation, okay, which basically follows from the first law of thermodynamics. So this thing, okay, this thing will be equal to what? This will be equal to the strain energy. We are concerned with the beam. Specifically, this is a case of bending of beams under a concentrated load. or a point load. So earlier we had obtained various expressions for the strain energy, various kinds of loading, axial loading, then next we had obtained bending moment, then we had obtained transverse shear, then torsion. So the appropriate thing which we need now is this bending moment, and the expression for this is integration 0 to L m square by twice EI dx. So this is the exact same thing which I will just literally copy paste from here to there. I'll just paste it here. Okay, this is our right hand side. This is the strain energy of the beam associated with this bending situation. Now, as before we have done so many times earlier, what we are going to do is we are going to take a little cut section and isolate the left hand side part of it like this. This is our force P. Okay. And then we have the internal bending moment like this. This is M, and this is so you'll also have a shear, but I'm not writing it. I mean, you can write it. There's no big issue. Okay, so we have a shear like this. Okay, but I'm actually interested in finding the expression for this M. So this M will be simply minus of Px. So we substitute this expression back here, and we are going to obtain this as P square x square. Now you see this integration can very easily be evaluated, because with respect to x, P is not changing, E is a constant, I is just a geometrical property associated with the cross-sectional area, and it is certainly not changing with x. At least in this example, where the cross-sectional area of the beam is constant along the length of the along the length, this I is not changing. In a more general situation where you have a tapered beam or non-prismatic beam, I will definitely be varying with x, and then you cannot take this out of the integration like that. Okay, but here situation is simple. So we have this thing coming out of the integration, and we are left with integration 0 to L x square dx. So this simply gives us P square L cube by 6 EI. So we wish to find out the expression for delta. So delta will come out as PL cube by 3 EI. So see, I have stated the name of this topic as the limitations of the conservation of energy principle, but as the first thing that I have demonstrated to you is the wonderful way in which the conservation of energy principle actually works. Okay, so where it is working wonderfully well. The amount of effort you had to invest in solving the differential equation back in the deflection of beams chapter to determine the deflection at this point, compare that effort with the effort that you have actually done in carrying out the little algebra and the little integration here. Okay, so this delta expression, same expression you had obtained there earlier, here also same. Answer is matching, but the effort invested, there is a significant difference. Okay. Nevertheless, okay, despite this thing, despite the really easy way in which this has come out simply by the direct application of the conservation of energy principle, basically the equivalence between work and strain energy, despite this easiness, okay, I'm telling you that there is a severe limitation of this conservation of energy principle. So what is that limitation? Okay, so I have demonstrated to you the good thing about it. Now I'll demonstrate to you what is the limitation. So we are going to consider another cantilever beam. But this time, instead of one force, I'm going to apply two forces. This is P1, this is P2. Now, my question is the same as before. Okay, my question is that I want to find out the deflection at this point of application of the force P1. Alternatively, I may as well ask what is the deflection at the point of application of this force P2. And the only method that I'm now allowed to use is the conservation of energy principle. So dutifully, I will write down on the left hand side the expression for the work done due to the forces, and I'm going to write down the expression of the strain energy on the right hand side. So let me do that. So earlier when there was one force involved, I wrote this as half of the force times the deflection at that point. So here one force is P1, so this is P1 times delta 1, because delta 1 is the deflection which is occurring here. Similarly, I will have another delta 2 here, so I'll just add them up. So this is the total work done, and this thing on the right hand side will be again this expression. Now at first sight, some students may think that the limitation here is that compared to the previous case, it is a little bit difficult to obtain the expression for the moment when you have forces like this. And just a second. I mean, that's why, things are difficult. Okay, so but actually that's not the case. Okay, and in a more general situation, when you have more number of forces, it becomes really difficult to find out the m, and that is why it is a limitation. But actually that is not the limitation, that is only a difficulty. Okay, had that been the limitation, that would have been overcome, through some just algebraic effort. But the limitation is there that this equation is actually not solvable. It is not solvable because you have two unknowns here, delta 1 and delta 2, and this is just one equation. You have one equation involving the two unknowns, delta 1 and delta 2. Okay, so you need another equation. Okay, we need another equation to solve for delta 1 and delta 2. So this is one of the limitations. Another limitation is that suppose you consider the previous example only. Okay, we go back to the previous example where you have just this prismatic cantilever beam and you have just this single force. So we had demonstrated earlier that this works beautifully with the conservation of energy principle. There is no problem. But now I'll just change the problem statement a little bit and ask that instead of determining the deflection at this point, suppose I ask you to determine the deflection at any other point where no force is applied. Now you know for a fact that when this force is applied, this entire beam deflects down. And when it deflects down, various points along the beam do indeed have non-zero values of deflection. So it is actually a valid question to ask that what is the deflection maybe at the midpoint, or maybe at a distance of L/4 from the wall, or 3L/4 from the wall, or for that matter any other length from the wall. Those are all valid questions to ask. And when you are solving the deflection of beams, when you are studying the deflection of beams, it is true that you had to invest some effort in solving the differential equation. But the moment you solve the differential equation, you have the entire information in your hand regarding the deflection at any point. So that is like you put in some extra effort, you also get some return of investment. Okay, so it's not a pointless exercise to study the deflection of beams chapter. So this is the limitation of the work. These are the limitations of the conservation of energy principle. Okay. Now it may seem to you that, this is the end of the discussion, but actually no. Okay. We can still, push forward and utilize a, another principle, which is uh, like another version of the conservation of energy principle. Okay, uh, so this is what we are going to turn to now. Okay, and this something that we are going to turn to. This is like the bedrock foundation of many of the things which you are going to uh, study later on. Okay, uh, so let's launch into this. Okay, so the name of that principle is the principle of virtual work. Okay, some of you may have already heard of this in the context of other studies, or maybe you have not heard of it, but no matter, we are going to study it. The principle of virtual work. This is one of the most foundational things that you are going to study in all of your studies of mechanics in general. Okay, in general, mechanical engineering actually. So what is going on here? What is the principle of virtual work? So what we'll do is that uh, we will start our discussions of the principle of virtual work by going back to this W is equal to delta U equation only. Okay, so we'll start with this one. This is what we have been using. Basically, this is the work energy equation or the conservation of energy principle. Okay, uh, obtained from the first law of thermodynamics. And remember that, so this is the key point. Okay, so there are a number of important statements that I'm going to make, very foundational, uh, like fundamental statements. So please listen carefully about this. So this delta U, this is the strain energy. And remember how this strain energy came about? This strain energy came about because we said that the internal forces were conservative in nature. Okay, so this strain energy is actually equal to the negative of the work done by the internal forces. Okay, so since this is being recorded, I'm not going to write long sentences. Otherwise, it'll the lecture will also drag on too long, and I'll have to write an immense number of words. Okay, so rather I think you listen carefully to this and pick up the basics. So let me repeat, this delta U is the strain energy. So this is the potential energy associated with the work with the internal forces, with the conservative internal forces of an elastic system. So we can kind of uh, reverse our idea here and fall back on this expression of the internal work done. You have a minus sign here because it's something like this, that uh, the W is equal to the minus of the change in the potential energy. Okay, I believe you are familiar with this thing from your +2 studies. Okay, so I'm not going to invest any more time on this. But if you don't remember this, I suggest that you go back and maybe check up with your NCERT textbook, or maybe H.C. Verma, or any other standard good physics textbook. Okay, so we have just kind of written this in reverse. So what is this W then? Well, this W is actually the work done by the external forces. So although earlier we had not written it, now we got to make this clear that this W is the work done with the external forces. So this subscript E, this E stands for E external. This I stands for I internal. Okay. Now, although we have written it like this, by appealing to the conservation of energy principle, which was written in terms of the strain energy, uh, the moment we write this WE is equal to minus WI, this is actually a very general expression. Okay, so the moment you write it like E is equal to minus WI, Okay, this is a very general expression, or you can think of it like this, that WE plus WI is equal to 0, or in other words, the total work done by the external and the internal forces as part of a mechanical process, that is equal to 0. So this statement, okay, this statement is not the principle of virtual work because we have not yet introduced anything virtual in it. Everything that is going on here is still very much real. Okay, please note this. Nothing about this principle of virtual work has been introduced till now. Okay, I'm coming to that. But right now, whatever I am writing, this is associated with everything real. Nothing virtual has come here. But the important point to note at this juncture is that this statement involving the total work done by the external forces and the internal forces on a mechanical system as it undergoes a process, this statement is much more fundamental compared to this previous expression previous equation which we were working with. Because earlier when we wrote this, WE is equal to delta U, that was under that was under the limitation that you necessarily had to say that the internal forces were conservative in nature. But when you write like this, there is no restriction on that. These internal forces need not be conservative. If it need not be conservative, then it opens up the possibility that this kind of an equation will also be valid for a non-elastic mechanical system. I repeat, if writing this equation is much more fundamental and more general than this, because as I'm saying that you are freed up from the requirement that the internal forces have to be conservative, which is only when you can write something like this. Because it is free of that requirement that the internal forces are conservative, or just saying that internal forces may be non-conservative, meaning that it means that we are free to apply this equation even for non-elastic mechanical systems. This is an extremely important point. Okay, so this equation is more general than this one, and it is applicable even to non-elastic systems. Non-elastic mechanical systems. Okay. All right. Now we want to come to the principle of virtual work. So what is this virtual work? Okay. So when we say virtual work, there are two ways of looking at it. So we can have virtual work associated with virtual forces. So let me first state this thing, virtual displacements. And the other option is that the virtual work may be associated with virtual forces. So when we say like this, what we basically mean is that, see, work is force times displacement. When we are considering virtual work, you either make it virtual displacement times real force, or the other option is that you consider virtual forces times or multiplied by real displacements. I repeat, virtual work can be realized by two ways. One is virtual displacements multiplied with real forces. The second option is that you take virtual forces multiplied with real displacements. Some of you may be mischievously thinking that, okay, what about the other possibility that virtual work is like something like virtual displacement multiplied with virtual forces, that has no meaning. Okay, I mean you can just fabricate something like this, but something like that will never be used. Okay, and there's a reason for it. It's not something like we say that it is never going to be used, so it's not going to use. It's not like that. Okay, and there's a whole lot of very fundamental uh, mathematics involved with these things. Okay, like there are theorems after theorems associated with these things. We are hiding all of those details at this level from you. Okay, as you go on to higher level studies, you will find that you will still not encounter theorems and everything, because when we say higher level at this stage, we basically mean maybe fourth year and maybe fifth year for dual degree students, maybe even the master's level students. Even at that level, we don't expose you to theorems like this. Maybe if you do actual PhD work in these kinds of things, like involving hardcore continuum mechanics and elasticity theory and like hardcore advanced mechanics of solids, then maybe a little bit of theorems and things like that will be you will start getting the flavor of that. Okay, but until that time, or unless you choose to do so, you will never have to deal with those things, and that's absolutely okay. As engineers in training, you certainly don't have to become a mathematician. It's good to be, I mean, as good in mathematics as possible, uh, but you don't have to go down that route, uh, and certainly not for solving problems which are of engineering interest. So our approach here at the second year level of mechanics of solids will be to learn virtual work, not like a mathematical thing, rather like an implement or a method to solve uh, real problems, uh, like realistic engineering problems, uh, with the motivation that will somehow make our life a little bit easier. Okay, that is the fundamental motivation here. Okay, this is not just something fancy we're picking up because we can do this. Rather, we want to pick this up because there is a promise here that it is going to make our life a little bit easier. Okay, but before we can do that, we have to learn a few things. So that's what we are going to do in the remaining of this discussion. So let me go to the next page and start the discussion on the principle of virtual work based on the virtual displacements. By the way, I have not actually stated the principle of virtual work. I have only said virtual work may be associated with virtual displacements, one option, and second option is virtual work may be associated with virtual forces. But what is the principle of virtual work? Well, the principle of virtual work is just this statement again, external plus internal contributions together, but external and internal contributions using the virtual work. So the virtual work uh, considering the external things, the virtual work considering the internal things, that together will be equal to 0. Okay, so statement wise there is not much difference, but in terms of how you interpret it and how you actually use it to solve the problems, it makes a world of difference between the real work and the virtual work, and you will see that. Yeah, I mean, shortly you will see that. So let me go to the next page. Uh, Virtual work based on virtual displacements. So meaning that we'll be multiplying real force with virtual displacement. So uh, we will talk about the kind of deformable solid bodies which we have been talking all along in this chapter, in this course, but for the sake of illustrating or demonstrating to you what we are talking about here, this principle of virtual work based on virtual displacements, I will take something which we are all very familiar with, which is a spring uh, mass system. Okay, many a time, like many times we have encountered this and we are going to take it up. So this is our spring. Attached to the bottom of this spring is this mass. And we say that we have applied a force here, and this part is very crucial. Okay, so what we say here is that this force is there, okay, and this is in an extended fashion. The spring is an extended fashion, but this extension is not a real extension. Okay, it's not a real extension, rather it's a virtual extension. So it is only in our thoughts that we have extended it. What do we mean by that? Only in our thoughts we have extended it? What we mean by that is that if you perhaps just leave this spring, then there is going to be maybe some sort of an oscillation initially, and the force here is going to change with time or something. Now, we are not bothered about those things, okay? So when we, and this is a very, very subtle thing to pick up. So if you are a little bit confused as I say these things, I mean, don't feel bad about yourself, okay? You are supposed to feel a little bit confused initially. So it's like this, that when we impose a virtual displacement, what we say is that the real forces, they remain constant. Okay, they remain constant. They do not change. It is something like we are kind of freezing up time, and in that frozen snapshot of time where the forces and the constraints, they are not changing, in that frozen time snapshot, we are imposing this kind of a virtual displacement. So the displacement that we are going to say here will be depicted through this kind of a notation. So in reality, it would have been a delta displacement, but we are not doing this in reality. We are only doing this in our thoughts. So this delta, this expression, so this is like the Kronecker delta. Okay, so but this doesn't have the meaning of Kronecker delta here. So this is just a thing. Okay, just a symbol. So this symbol, it represents that this displacement is a virtual displacement. Okay, and just saying that it is in our thoughts doesn't make much sense mechanically. What we really mean is that we have frozen up time, and in that frozen snapshot of time, when we are implementing or imposing this displacement, then the forces, they are remaining constant. Okay, had we imposed a real displacement, then in general the forces would have changed. Okay, of course it would have changed. Okay, because your spring force here, that very much depends on how much the displacement is here. Okay, but that we are not doing. We are just imposing it like this. Now, suppose we draw the free body diagram of this mass here. So we have this force. Let's say this is P, this P, this P, and this, like this P is very much real. Okay, this is a real force. Correspondingly, the balancing force on the other side of this mass, let's call this F, that also is a very real force. Okay. Furthermore, if you just consider the spring, that will be experiencing a force in the downward direction having a magnitude F. Okay, you see the force on this thing is pointing upward and this force on the spring is pointing downward. Now you may almost fall asleep by me highlighting these things, but these small things have play a major role in what I'm going to discuss next. So it's like this. Earlier we had said that W is equal to minus Wi. But now we are not working with real works. Okay, we are not involved with real work. Rather, we are involved with, or we are concerned with, virtual work, because the displacement that we have imposed is a virtual displacement, which is why this virtual work is based on virtual displacement. This virtual displacement is going to be multiplied by the real forces that are there. So instead of this equation, we are going to use the virtual version of this equation, which is delta of WE is equal to minus delta of WI. As mentioned earlier, just a bit earlier by me, that this delta, it represents the virtual nature of the displacement here. Similarly, this delta here in front of the WE represents the virtual nature of the work done here. Similarly, this delta here represents the virtual nature of the work done here. On the left hand side, we have the virtual work associated with the external forces. On the right hand side, we have the virtual work associated with the internal forces. What is this internal force? This internal force is this F. What is this external force associated with WE? This is this P. So can we not perhaps write that this delta WE is nothing but P times this delta delta or del delta. This one, so this minus as it is from here, this delta WI, what I'm going to write this as is minus F of del delta. The reason I'm writing this as minus F is that you see this del delta is actually being imposed in this direction. Okay, although I have just written it like this, that this is the magnitude, but actually this del delta is, it is imposed in this downward sense. Because it is imposed in this downward sense, this P and this del delta, so if you want to think of it like that, work done is like F dot R, it's actually a dot product, then because they are in the same direction, so the external work has a positive sign in front of it, but this internal force F, this green colored internal force F, when it is being multiplied with the del delta, it is with a minus sign because this F is upward and this del delta is downward. Okay, that is why this minus is here. So overall, we end up with P del delta is equal to F del delta. Now this del delta is same. Okay, in fact, you can perhaps argue like this, that you obtain from this this. So you have two options here. Either P minus F is equal to 0 or del delta is equal to 0. Now del delta equal to 0 is a very specific case. We are not interested in those specific cases. Rather, we want del delta to be something arbitrary. And because we want del delta to be something arbitrary, it naturally leads to the condition that P minus F must necessarily be equal to 0 for this entire thing to be equal to 0. I repeat, because this del delta may take on arbitrary values. Okay, whatever we have done here, it will be true for any imposition of or any value of the imposed virtual displacement. This can take on any value. So the only way that this equation is going to be satisfied, despite del delta taking arbitrary values, is when P minus F has to be is equal to 0. So this is the thing, that P minus F is equal to 0 or P is equal to F. Now you may think that we have gone to such extreme lengths, like trying to kill a mosquito with a rifle, okay, just to write that P is equal to F. But please note that this is deliberately the simplest of examples picked up only for the purpose of demonstration. In an actual problem, you will have certainly more involved situations, and that is where you will begin to realize the great benefit that these ideas will afford us. Okay, now just for the sake of completeness, let me state that because when you when you start out with the principle of virtual work based on virtual displacements, you end up with this kind of an equation where there is basically just a force balance, which anyway you would have obtained from the condition of static equilibrium. Like if you just take your y-axis along this vertical direction and you say that sigma Fy equal to 0, immediately by closing your eyes, even students who are just preparing for starting for JEE preparation, maybe they will sit for 2 years down the line, even they will tell you that this is P equal to F. So this is just a simple case of the equation of static equilibrium. Okay, so the Principle of virtual work based on virtual displacements is just another way of arriving at the equation of static equilibrium. It's an equivalent statement for that. Okay, remember this. Next, we are going to pick up the virtual work based on virtual force. So as you may guess, this time we are not going to impose a virtual displacement, rather we are going to impose a virtual force. So we are going to pick up, or we are going to consider again this exact same mechanical system as earlier, consisting of this spring, uh, and here we are going to impose this delta P. We are again going to isolate this mass out and say that this delta P is here. Correspondingly, you will have a counterbalancing force, specifically a counterbalancing virtual force delta F, and you are going to obtain for the spring the same kind of situation like before. Okay, please understand that I'm trying to draw the same kind of spring that I have drawn on the left hand side, and you will have a force like this, delta F in the downward direction. Now, if I consider this mass, I again use my principle of virtual work, which is just this statement. And this one I'll be able to write as delta P delta. Please note that this delta is the real delta. Okay, there is nothing virtual about this delta. This delta P is the virtual force, which we are kind of imagining to apply here. But this delta is the real displacement. And on the right hand side, we have correspondingly this delta F. Now this delta is the delta of the spring. Okay, so we are deliberately making this very pedantic or very formal kind of thing, but please note that in terms of the level of formality that can be done associated with these things, this is nothing. Okay, this is a very dilute thing, but it helps us to understand these things at the second year level, which is why I'm making it like this. Please also note that if I remember correctly, none of these things are present or in this fashion uh, either in the book by Beer and Johnson or the other book from which I usually give problems, that is Hibbeler's textbook. Rather, I have taken this part of the presentation associated with the virtual work from another book, much older, which used to be kind of a textbook in our time. It's by Igor Popov. So let me just write it. Engineering Mechanics of Solids by Popov. It's an extremely good textbook. The only disadvantage is that it is written in a very boring fashion. Okay, especially when given to undergraduates, it tends to make them fall asleep. Okay, so it's a very seriously written book, and well, it's what it is. But this particular presentation is given in a very nice fashion. Okay, now what we are going to say here is, okay, so let me just write this one more step. It's like this. Now we know a priori. Okay, so this is where we are going to use our knowledge of mechanics, that we know a priori that delta P is equal to delta F. So here we are actually allowing ourselves this knowledge from mechanics. Mechanics means Newtonian mechanics. So delta P is equal to delta F. And so what we conclude from here is that delta of the mass should be equal to delta of the spring. Now this seems like rather ridiculous. Okay, of course it is equal to delta spring. I mean, did we have to do all these things just to arrive at this? And did Popov like is he famous for these kinds of things? So it's not like that. Okay, again I'm telling you, these are like the very basic building blocks. Okay, so uh, try to wrap your head around it, not by uh, allowing yourself like a complete freedom to think about these things, rather try to think about these things in the step-by-step formal way that I'm trying to expose it to you. Okay, and because when we proceed by this method, the virtual work based on virtual force, we end up with this kind of an equation which basically tells us the uh, the the compatible displacements that should be occurring so that these things do not break apart. This is just a recipe. So this virtual work based on virtual force is just a recipe for arriving at the equation of compatibility. Again, I'm telling you that there are, I mean, more sophisticated versions of these things. I'm just not going into all those things. But before, so it is now time for us to go into uh, the actual steps which we will have to take up in order to solve the problems. Okay, but before I can do that, I'll go back to the previous page and tell you about something very nice. Very nice means it's nice as well as, I mean, a little bit confusing sometimes to some people. You see, we have started with this delta WE is equal to minus of delta WI. But suppose you were to consider the force, the capital F force, not this one, rather this one. Then this point is also coming down by this displacement, this imposed displacement delta delta del delta. So we might as well have considered another version of this principle of virtual work where we say that this is like this, but we consider the work done so due to this force. Okay, so this is this IE is uh, just to depict the fact that this internal force is exactly aligned up with the external force like this. Okay, this internal force is in the opposite sense of the external force, but this version of the internal force looking at the spring, that is aligned with this force P. So this E for external together with the I for internal, it just depicts that thing. So we are still looking at the internal things, but kind of from the point of view of the external force. The only good thing about it is that we have managed to get rid of this minus sign in front of it. Okay, and that makes sense actually if you write the work done associated with this, because please note that this will be F, because if you see here, this F is here, this F multiplied with del delta. You don't have to actually write the minus here. Okay, because F and del delta are in the same direction, and this one is P del delta. So these two things are actually equal. Okay, so if you go back to this thing, this is what you were getting. P del delta is equal to F del delta. So there's nothing new that you are obtaining here. It's just a different way of looking at it. Okay, now why I'm saying you this is that in many books, without telling you clearly about this thing, which I just told you, that you just look at the internal force from a different perspective, without telling you this statement explicitly, they will just write that the virtual work associated with the external forces is equal to the virtual work done by the internal forces. That is a highly misleading statement. It is not equal. It is, I mean, kind of equal in magnitude, but opposite in sign. So this is the actual real statement, because this is what leads to the fact that uh, the total virtual work is equal to 0. Okay, but in some textbooks you will invariably find that it is written rather carelessly that the work done associated with the external forces is equal to the work done due to the internal forces. Like people will actually write like this, that delta W external is equal to delta W internal. Okay, so this is not true. Okay. It is true only if you interpret this right hand side in this fashion by considering the force, the internal force aligned up with the external force like this. Okay, so there is a very, very subtle difference which you must appreciate. In exactly the same fashion, if you go back here, you can try to think of it like this, that you have a delta WE is equal to minus delta WI, and this should be equal to delta WIE. Okay, and you will have the corresponding expression for here. So I'll not spend any more time, repeating this thing. So when we are going to apply our steps for using the virtual work for various problems, it is in this sense, this delta WE is equal to delta WIE, that we are going to use it. Okay, so let me go to the description of the steps. Just take a sip of water. Okay, so we want to use the virtual work associated with the virtual forces as a method for finding out the deflections. Okay, so virtual work associated with virtual forces as a method for finding deflection. Okay, so understand, so remember this, we are talking about virtual force. So the second discussion that we just had, virtual forces. So for the virtual work, we are going to multiply these virtual forces with real displacement. This is the real fundamental thing here. Okay, so and I again want to highlight here is that this method, because it is associated with this virtual work and we are not talking directly about the strain energy or anything, this is a very general method, and it can be, once you learn it, you can equally apply it to elastic systems as well as non-elastic systems. Okay, so this is a really good investment of your time and effort to learn this thing. So what we are going to do is we are going to consider a general three-dimensional deformable body like this. This body, let it be having these kinds of supports. There's a ruler here, there's a pen here, and let it be subjected to this force, one force here and another force here. And the intention here is to determine the deflection at this point. More specifically, we wish to determine the deflection at this point along a certain direction, this. Okay, this is the problem. Now you may think, what kind of like an artificial problem is this? Okay, where will you find this kind of a potato shaped body, and where will you find this very specific, like you find deflection only around that direction? So just think of it. The earlier problem which we had said, or which we had given as one of the examples for the limitations of the conservation of energy principle, was just a specific example of this general situation. Because if you just go back to it, here you see we have a general three-dimensional body, which is our cantilever beam. We have two forces on it. There is some support for this three-dimensional body, and we wish to determine the deflection either at this point or at this point along a certain direction. Now, you never thought about the direction because I just said deflection, and you were happy to note that because your brain had been already kind of primed to think of deflection only in this vertically downward direction. So now that we are stating things in a nice general formal way, it makes sense for us to actually specify that when we say deflection, we really intend to say that we want the deflection along a certain direction. For this kind of a cantilever problem, we are interested in deflections in the vertically downward direction, either at this point or at this point, or perhaps even at any other point. Okay, and you will see that the virtual work method that we are going to learn, that will be absolutely fine for us to find the deflection at any point. Okay, not just at those points where the external forces are applied. So what are the steps? So these steps are almost like an algorithm. You follow them step by step, you will get the answer. Okay, and if you try to think about it a little bit, you may feel confused initially, but as you keep on working through the problems and maybe try to turn this over in your mind again and again, you will see that things will start to fall in place. So let's start with the first step. First step is that you consider the three-dimensional body, but you consider it to be completely unloaded. So basically you remove this force, you remove this force. Okay, so what we are going to do is consider this. Nothing got picked up. Okay. So we consider the unloaded body. And we apply a virtual force of unit magnitude along this direction. A virtual force of magnitude 1. Okay, so we will say it like P is equal to 1 along desired direction, along the desired direction. So our desired direction was along this yellow dotted line. We will apply our virtual force. Let's say this one, maybe this one, yellow. Okay, so we say that this is delta P. Mind you that the magnitude of this P is equal to 1. Okay, in fact, I should write this as delta P is equal to 1. Okay, with the understanding that this 1 is like a virtual force. Okay, it's not a real force. All right, so now you understand that when we are applying this force, no other force is there. This force is going to induce a distribution of internal forces within this, all throughout this body, this general body. Okay, so you calculate those internal forces. So due to delta P, internal forces generated all throughout the body. And as long as the body is statically determinate, we can find out the values of all those internal forces. Like if you wish to find out the internal force here, the internal force here, the internal force here, anywhere, you can find that out. Okay, so due to delta P, you will end up with a distribution of internal forces all throughout the body if you calculate them. Okay, so if the body is statically determinate, we can determine them. We can determine all these internal forces. All right. So next step is what? So you have applied this this delta P, you keep it applied. Now you uh, bring back the actual loading, meaning that you bring back this force and this one. Okay, so with delta P still applied, bring back the actual loading. That is the all the forces that are present. Okay. Now this actual loading, it will lead to certain deformations. Okay, so this actual loading will lead to some real deformations. Okay, this real loading, so real deformations. Calculate this. Okay, you calculate all these real deformations as due to this actual loading. Okay. Now, when I'm writing these statements using these words, it may seem like I'm actually ending up doing more work, perhaps using these energy methods, but it's not like that. Okay, so you'll see in the while doing the problems, uh, some of the problems are like beautifully suited for the application of this virtual work. Like any other method you use, you will end up doing much more work. Okay, uh, like actual effort that you have to put in, it will be much more compared to energy methods effort. Okay, so the next step, step number 4, this is the crucial thing now. Well, every step is crucial, but this is the one where you actually determine the thing. So what you do is you determine the external virtual work by multiplying the external virtual force, that is the force delta P, with the real deformation which is acting at that point. So uh, so write the external virtual work uh, by multiplying delta P with delta, that is the deformation along the desired direction. Please note the very important concept involved here. You see, when you are uh, when you are looking at the original problem, due to this loading, there is a certain deformation along this direction. Okay, there is a certain deformation along this direction. Now, the way that you have started solving this problem is by taking a delta P along that direction. So when you are finally doing the work, calculating the work done, you are supposed to multiply this delta P with the deformation which is taking place along its direction, which is relevant at this point. But that deformation is nothing but this delta which you are intending to find out. Okay, so please try to understand this important thing very clearly. Okay, you want the delta, which is the desired deformation, the deformation along the desired direction, and it just so happens that you have framed your solution steps in such a way that that is the deformation along the direction of the imposed virtual force delta P. So this is on the one hand. On the other hand, you calculate the internal virtual work. You write the internal virtual work sorry due to all the internal virtual forces multiplied with the deformations at those points along those internal force directions. Okay, so it's something like this. So uh, if you draw this thing, if you maybe draw this thing again, maybe this entire thing. Okay, so here we are seeing this thing. So corresponding to the step number 2, we have this. Corresponding to this, we have this picture that due to this delta P, if you take any little element internally, there will be a delta F present along this direction. And when you go to the step 3, then uh, with this delta P still applied when you are bringing back the actual loading. So if we copy this thing again, maybe I'll draw it here. So same situation as before, but now we are applying this thing, applying this force here and this force here. Can't get this force right. The writing pad has become a little bit slippery, it seems. Okay, so this thing is getting extended. Okay, well, extended means it is getting deformed, this element, as a result of this these applied loadings. And let's say that the deformation associated with this little element is u. So all in all, what you are going to end up with at the end of this step 4 is an expression like this. Delta P times the actual deformation which is taking place at that point. This is on the one hand. So this is the first statement on the left hand side. For the right hand side, this statement, the internal virtual work due to all the internal forces. So internal forces is delta F, and this will be multiplied with the deformation which is corresponding to that force. But please note that this is just one element. So we should be summing up over all such elements. Okay. Now, written like this, it may seem like a rather impossible task. Like, how are you going to account for all the little elements which are present here? This seems rather daunting. But let me just tell you that this can get cleaned up very easily if, for example, you consider something like a truss. Okay, so uh, if you have a truss, okay, just a very simple example, simplest of examples. If you have a truss, then uh, you please note that this delta p is like a 1. Then at maybe one of the nodes in the truss, you apply this virtual force of magnitude 1, and then you multiply with this delta. So let's say we consider a truss like this. Okay, and let's say it's something like this. And maybe some loading is there, maybe some loading is here, and we wish to find out the deflection here. So we can apply a this delta p equal to 1 here. Okay, now when you do that, you are interested in the deflection at this point. That is the delta. So you are doing just like this, 1 into delta. And on the right hand side, we have to write this thing. Now, this seems rather impossible to do, but it's not so bad actually, because you can clean it up a little bit by noting that all of these are two force members, and these two force members, they are basically axially loaded, and you already know how to determine the deflection uh, for axially loaded members. That is something which you have learned in your first year. Okay, so deflection associated with an axially loaded member is basically like NL by AE. So N is the actual force on that axial member, length is L, by A is the cross-sectional area of the member, E is the Young's modulus. So we have to consider each of the truss members one by one. So this summation is from 1 to n, where n is the number of members. So here the number of members is 1, 2, 3, 4, 5, 6, 7. Okay, so 7 members, so you have to do that thing. So your job is not very easy, but it is not that difficult also. Okay, as compared to the fact that suppose you had to solve this problem without taking recourse to energy methods, how are you ever going to find out the deflection here? That seems even more daunting. At least now you have some recipe of determining the deflection at this point. Please also note that, by the way, this is I also. Please also note that in each member, when this, if you had removed this loading, due to this applied loading delta p equal to 1, each of these members, in each of these members, there would have been developed a force corresponding to this delta p equal to 1. That force is this delta Fi. So in each of the members, there will be a force associated with this delta p equal to 1 in the absence of this. Okay, so that's a relatively easier problem, like a relatively easy problem to do. From your first year basic engineering mechanics funda, you can determine that delta Fi. And in each of the members, there will be a deformation like this, not due to this one, not due to this one, but due to this one. Okay, so On the left hand side, you basically have delta because this is just 1 multiplied with delta. So you have in your hand a recipe for obtaining the entire deformation. So the deformation at this point in the desired direction. That's it. Okay, so this is for a truss, of course. You will have other examples uh, like uh, beams. Okay, so for beams, it will be something like this. Beams, considering bending, it will be like 1 into delta is equal to, well, this sigma will then become an integration. So uh, plus this thing is going to become, so let me just write this thing. Okay, yeah, you'll see. So what have I written here? So you see this thing delta F into U. This is force into displacement. Equivalently, we can also think of it in terms of a moment into an angle, because a moment already has the dimension of Newton meter. So delta F into U has the dimension of Newton meter. If you write this equivalently as delta M, a moment times a theta, that also is like a work done. So a bending moment multiplied by an angle expressed in radians, that is also a work done. Now this thing can very easily be written, this theta. Why? Because this theta, you see earlier we had, so let me just take this to the next page. So we had this expression that we had derived earlier. So if you don't remember this, go back to the chapter on bending, you will see that this is there. So this R is the radius of curvature. So this R is like EI by M, or you can think of it like this. This is 1 by R is equal to M by EI. Now, if you have an arc of the beam like this, then you have S is equal to R theta. So remember this kind of a diagram that we had drawn earlier. We have this beam, this little length of the beam. So if this arc is S, it has the length S, and this radius of curvature is having R. Okay, so this is R. So this angle is theta, then S is equal to R times theta. Okay, so our theta, it becomes equal to S by R. So here S is like a length of over which we are concerned, length of the beam that we are concerned with. That length is nothing but this dx. Okay, so this S does the job of the dx, and this theta is this theta. So we basically have theta is equal to S by R, and this 1 by R is nothing but M by EI. So this is equivalent to M by EI for the 1 by R, and for the S, this is dx. So this expression becomes small m times M dx divided by EI. And you can just write this dx, it will be clearer. Now the question is, what is this M? Well, earlier when I was explaining this thing, I said that this delta F is the force, is the internal force that will be generated due to the application of this virtual force of magnitude 1. Here also correspondingly, this small m is the moment that is induced in the beam due to the application of this force of magnitude, this virtual force of magnitude 1. So for instance, if you have a beam like this, and let's say that it is subjected to maybe a distributed loading. Uniformly distributed loading, and you wish to find out the deflection at this end, or maybe at this point, or at this point, anywhere. Okay, all that you have to do is apply a virtual force at that point, whichever point you're interested in, and in the unloaded condition, and correspond to that virtual force applied at the desired location, you can determine the bending moment anywhere within the beam. That small m is that m. Okay, so the bending moment associated with the uh, virtual force of magnitude 1 that you apply. So just to make it clear, if you remove the loading, consider the beam, and let's say that you desire the deflection, let's say maybe here only, okay, at this end, then you apply your uh, virtual force at this point, and then anywhere in the beam you will obtain the expression of this small m as this minus delta p into x. Okay, just like before. So this m is corresponding to the virtual work, virtual force in the absence of the applied loading. Okay, in the absence of the applied loading, this is the virtual force all along the beam, and this m by ei is just the expression for the theta. So overall, this is giving you the work done due to the or the virtual work associated with the internal forces. And here also you have directly a recipe at the end of obtaining this deflection, provided you substitute the appropriate values here. So this is certainly an alternative way of finding the deflections. But of course, if you are really comfortable solving differential equations, go ahead and go by that method. Okay, but I think there is a significant return of investment if you put the time and effort to learn these energy methods. Okay, so as the situations become slightly more complicated, you will see that these energy methods will pay off. Okay, there's a reason why they are so popular, especially among the students also. Take in my very end of the previous lecture, I'll just correct it in 2 minutes. So correction is like this, that I go back to my writing app. So this thing I had written as m theta dx, and then this theta I had replaced by, I said that theta is equal to m dx by ei. Now if you replace this theta by m dx by ei, you end up with m dx square by ei. So definitely something has gone wrong here. And the mistake is that this thing should actually be m d theta. Okay, and it is this d theta which is like m dx by ei. So sorry about that. That is the correction. So everything previously that I had discussed, that must be understood in that thing. So this theta is actually this d theta which we are talking about here. So this m d theta is the virtual work associated with the internal forces, this m, which is generated by this I1. Please also note that in the earlier lecture I had mentioned that this m as the virtual force, but please try to interpret that as virtual loading associated with the 1, because this is really a moment, okay, having the unit of Newton meter. So that's it. Thank you very much.